Good morning to everyone. This is the course that Professor Marathe and I will be teaching you, Industrial and Engineering Chemistry. I will be covering 3/4 of the class and 1/4 will be covered by Professor Marathe. That's the way it's distributed between us. I thought that first let me tell you broadly what will be the syllabus for the portion that I will be teaching you. These hours and things like that are just given in a very approximate way. It can change, so it's just a rough indication. First, of course, I will begin by giving you a historical perspective and overview of chemical industry, because that's very important. I don't want to just jump into that we have this technology, that technology, we practice this. I think it's also important to know where all these things came from. Were there certain triggers which led to these things actually gaining acceleration? And also, I think that as we go along, I want all of you to also think about whether these things are always going to remain the same. Things which look extremely mature, it looks like almost impossible that they'll be ever dislodged, but they do. There are so many changes taking place in the world. So that's very crucial. And so we need to really have a good understanding of sustainability of raw material, feedstock, and then energy sources, because so many of the processes will actually be driven by energy. And so it's very, very important to know about energy. And that is a very crucial area. And today, of course, the energy sources are not just crucial from the point of view of availability, but also from the havoc that is being created in terms of the environment and atmosphere. So there are very, very serious issues, and I think that I don't need to tell you. Every day you will read about it or listen to it on TV or on your mobile. Every day there are genuine concerns which are being expressed, and so we'll need to understand energy sources from now the twin perspectives of availability as well as from the environmental issues. Now, there is another, of course, very, very important part of the syllabus, which is to understand production choices based on resource availability. Every country may not have the same resources. Some people will have X and some people will have Y. So obviously, even if a process does not look extremely attractive, you may actually have to practice it simply because that's what you've got. So that's another thing that you please keep in mind. Although, of course, it's become a global world and you can source material from anywhere, but the truth is that someone can turn off the tap. And so we need to be very, very cautious about such things. Now, as you know, many of the processes which we actually practice in industry, there is a very prominent role of catalysis, in many of this, and we will see as we go along. So it's important that we also know what was the origin of catalysis, how did it actually come to be, who were the people who created these concepts, and which have lasted for so long. The concept of catalysis and the search for catalysts. It's so crucial. Without catalysts, many of the processes would never have been feasible. So we will look at that. We will also look at what are known as platform technologies. Platform technologies can be launched in many directions if you possess such technologies. Like, for example, it could be that if someone has tremendous expertise in enzyme processes, enzyme technology, maybe it can be applied in many different directions. So it would be like a platform technology of bioprocesses. And likewise, there are critical intermediates, and we'll cover that. Once you have obtained a critical intermediate, you can go in so many different directions. So critical intermediates is something that you should always keep an eye on, because that's what gives breadth to a technology. It's critical intermediates, and we'll give one or two examples of that. Critical intermediates could be organic as well as inorganic. So we will have a look, at some of this. Now, the chemical technology, particularly, world over, really runs on some bread and water chemicals. If you did not have those, then it would be very difficult to actually produce a lot of products. We don't think about it that way. Like, for example, fertilizers. They're so crucially dependent on, for example, sulfuric acid. It would be hard to imagine doing something without sulfuric acid. Okay, and likewise, there are numerous industries which are dependent on sulfuric acid in certain forms. It could be for sulfonation processes, a wide variety of other things like nitric acid. You require it to produce so many different nitration products, including weapons. Okay, they play a very crucial role. Okay, so we need to understand some of these very, very crucial chemicals. Likewise, what is the process by which sulfuric acid is made?
Contact process.
Very
Contact
good.
process.
Okay, contact process. Okay, but it's also important to know that it wasn't always that way. Okay, it was made actually by a different process before. Subsequently, it is that the contact process became important, and it's important to know the historical development, because at any point in time, like when, for example, let's say the chamber process, which preceded the contact process, when it was being followed, a lot of people said that no, this is a great process. it will possibly remain. No one thought that it's going to be dislodged. Okay, and likewise, when we look at the Haber process, we have got so used to the Haber process that it almost seems like it has been there from eternity. It hasn't. There were other breakthrough technologies, and let me tell you, there was a point in time when it was felt that no, those are the greatest technologies and they will remain. Okay? Nobody thought that they will get dislodged. Okay? So the reason why I want to stress this, and I'll do this repeatedly, is that you see, you are learning this course so that it is useful to you, and what will be useful to you is what will happen in future. Okay? And you must be prepared for transformation. You should not be uncomfortable if you suddenly see something else coming along, and it's very important. Otherwise, if you're not mentally prepared for the changes, you could be left way behind in the race. Because you'll think that no, everything is fine. Okay, but other people are moving ahead, and we are actually at that crossroad today. I envisage that in 50 years there will be such a massive change, which will take place, and this will all be when you all are probably just about 70 years old, and you might see the world has changed drastically. And so please keep that in mind, not to speak of your children and grandchildren. They may see a very, very different world, and people might almost express disbelief that these were the technologies that were being practiced in 2020. People might say, oh really, that's the way it was. You'll see this over and over again. It's also very important that we understand what are India's strengths and what are India's weaknesses, because India is in a precarious position in many areas, but it also has some strengths. One of those strengths is that we have a very long coastline. That's one thing that nobody can deprive us of, which is seawater. Okay. India also has a great strength in the sense that our climate actually allows us to carry out some processes which are just driven by solar energy. Whereas many other countries may not be blessed with so much sunshine, and they may not be able to do it. Okay, so those would be our strengths. And so it's very important to understand our strengths, and any country must capitalize to the fullest based on its strengths. Okay. Like if you have to barter chemicals, obviously, I will produce the chemicals that which I can produce here in abundance and others cannot. And so you may trade in those chemicals, and you may in turn get chemicals which you cannot otherwise produce. So I think it's very important that we look at that. And so I will be covering marine chemicals. What is the most important marine chemical that we have?
So salt.
Yes, salt. Absolutely. Sodium chloride. And India manufactures close to about 30 million tons of sodium chloride every year. We always talk about very fashionable, fancy things. But this is one product which is one of our largest products, salt. And salt is not just about eating. There's so many applications of salt which we need to understand. And frankly, if salt didn't exist, then those industries would not exist. And in turn, numerous downstream industries would have perished. That's the importance of salt. Likewise, seawater gives us other chemicals like bromine, magnesium products. And then, in fact, one of the fertilizers till until recently we were not producing at all in our country, potash, because we didn't have any other resource. But potash you can get from the sea. So it's vitally important that we strengthen these areas, and therefore I will be covering those. We, of course, are very familiar with the ammonia synthesis, as you all know, the Haber process. As I will show you, the Haber process was not there for eternity. It wasn't there till what? Till about 110 years ago. What is 110 years compared to the number of years that we have existed? Civilization has existed. It's nothing. And some of these things could come and go, or they could be transformed in very radical ways. And as we go along, we will try and see that. We'll also see how, for example, nitric acid is produced from ammonia, and of course urea, as all of you know. But this may not be the best way of producing nitric acid. I envisage that in future something different, and maybe it will be a reinventing of the wheel which will happen, and such technologies which become crucial. And you need to understand what actually dictates the choices. And if the choice of feedstock, if the choice of energy, etc., opens up or gets shut, then some of these things will transform very dramatically. And frankly, it's hard to see how civilization and populations will survive without essential fertilizers like urea. It's very, very difficult to conceive of that. But it might come to be that we'll have to look at these kinds of hard choices. Another very important fertilizer, as all of you know, NPK, is P. Our resources have dwindled. We don't have, and we are a population close to about getting to 1.4 billion people. What are we going to do? You'll find also that as we discuss, that the feedstock from which we get phosphate fertilizers has a host of other kinds of impurities, metals, fluorine. They could be playing havoc on the environment unless you remove them. Okay. On the other hand, they could also present an opportunity. that if you can recover those elements in the process of also making fertilizers. So that will be again something that we will discuss. We will also be talking about two of the very important things which again we take for granted. Water. You can either take water for granted or not, and don't be fooled by all the good rains that we are getting. There are many situations, where there is drought. There's no water, and again, because we have got a long coastline, we have got an opportunity to do desalination. So, that's one of the technologies that we will discuss, because it's going to become increasingly more important. But we'll also need to understand the downside, of doing desalination. As such, you can get abundant water. After all, countries like the Middle East, that's what they depend on. They have no other source of water. So it's so important, and India is also coming to that stage, where it's going to be very crucial that we find other ways of augmenting our freshwater supply. And another is that water, as you know, also is used by many industries, and finally they let it out. Okay, but many times, if they are being negligent, there can be serious problems of pollution. All the time, there are issues around the Ganga having become very polluted, very dirty. How is it all happening? It's happening because of a lot of residues, etc., from our agricultural fields, which are finally finding their way into the sea, okay, and the rivers before that. And also because of industries, when nobody is looking, they go and conveniently discharge their junk into the rivers, into the drains, and it goes all the way to the rivers and finally into the sea. That's how pollution is happening. So it's vitally important that we also understand how to clean up the mess. How do you really take care of effluent water? These are the two angles from which we will look at water. Now, I think that the COVID calamity has taught us one thing, that do not take anything for granted. You saw what happened when people were gasping for breath, okay, and there was no oxygen around. And it's so important that we understand that air is just 1/5 oxygen, and that is not enough if you are ill. Okay? Your body needs more purer forms of oxygen. Okay, and so we need to understand how oxygen is obtained. Okay, in relatively pure form. Oxygen is also required in many other applications, not just for health related issues. Like, for example, in the future, if you want to have combustion taking place more efficiently, you may want to do it with enriched oxygen. You might have a better quality of combustion, and that might be one of the ways of actually mitigating pollution and contamination that we have. Unburnt fuel, etc. All these problems we might be able to deal with. There are many other applications, and likewise nitrogen. So many processes require inert atmosphere. I can't have oxygen there, and the best way to provide an inert atmosphere is to remove oxygen. And you can see the complementarity of nitrogen and oxygen from air, how vitally important it is. And then you've got the other big advantages that these kinds of gases like nitrogen, I can cool down to extremely low temperatures. And there are so many applications of liquid nitrogen. Okay? And so we need to again look at it from that point of view, not just from the the industrial applications of inert gas, etc. It's so much easier to transport a liquid than to transport a gas, unless you have got very extensive pipelines. Okay? And so you can see, I mean, even from that point of view of transportation, how important it is that we look at the liquid states of these materials. We will also be covering uh, petrochemicals. If you look around, ours is a carbon world. There are huge problems with CO2 and all, but the fact of the matter is that today, whatever you look at, the clothes you wear, the medicines that you consume, you know, the pesticides that we use in our field, the fertilizer that we make, so many chemicals, things like acetic acid, methanol, they're all petrochemicals as of today. Maybe 30 years down the line, there will be a dramatic change that will happen. But as of today, petrochemicals are extremely important, and they had an air of invincibility about them. People used to brag, about petrochemicals. But let me tell you that we need to be very sober because the good times may come to an end, and we'll have to see how do we provide the same standard of living to people, and could there be a non-carbon world? Is it possible? I'm just being provocative, but these are things to see. Maybe one day your fuel will be ammonia. It will not be coal and natural gas. It's possible that there could be very, very major changes, and it could be driven by issues around climate and feedstock availability. Now, while we are also talking about energy, we will also look at one technology which will become increasingly important over the years. Okay? It's already very important. I don't think that, I think all of you have mobiles and laptop. All of you know that these have got batteries. But for the fact that you have got such wonderful batteries, okay, I mean, the charge would drain out in no time. Okay? So, battery technology is going to become crucial. There's a lot of talk about electric vehicles. You can't have electric vehicles without batteries. And so we will try and understand how battery technology has evolved over the years, and we will discuss the Nobel Prize that was awarded in 2019 to the people who invented the lithium-ion battery. But let me tell you that 20 years from now, there's going to be such a shortage of lithium, and that will happen because of many other competing requirements. That you may have to actually switch over to other material, maybe sodium, maybe magnesium, and it's already happening. Okay, so it could be that lithium is not tomorrow's technology; it's today's technology. Okay, but 20 years from now, who knows? Something else might come our way. That's broadly the syllabus for the portion that I will be covering. Now, what I will be doing is that I will send you a couple of books, for which I have the soft copy, which is the Chemical Process Technology by Molin, and also, especially for the introductory lecture, a perspective of the international chemical industry by this person, Fred Aftalion, who wrote this book while he was in University of Pennsylvania. But another very important book for which unfortunately the soft copy is not available. It's available in our library, but you might be able to order it, buy it. It's Outlines of Chemical Technology by Charles Dryden. I think he came from Ohio State University and spent a couple of years in IIT Kanpur. Those were the early days, I think in the late 60s and 70s. And it's remarkable that he ended up writing a book on chemical technology, which was relevant to India, and that book is still very, very relevant and important. If possible, see if you can procure this book. It's not that costly, maybe 500 to 750 rupees or thereabouts. See if you can buy it. And of course, at the end of each of my lectures, I'll send you the lecture, and I record my lecture, so you will get the recorded lecture. Plus, I will send the PowerPoint and PDF of the slides. Okay, and also some related material. Some of the related material which I have actually drawn upon to prepare my lecture. I will send those over. Let me also tell you that it's very interesting that the more we talk about internet and free access and all, the truth of the matter is, I've been noticing over the years that things which were very easily accessible information, today they'll ask you to pay. Increasingly, it is becoming difficult to access information which is useful information. There's a lot of also not so useful information, which is of course flooding the internet and is there, or superficial coverage of things, but things which were covered in depth, and you would have thought that should be available to the masses and everyone. That's not necessarily happening. If it's going the other way around. So information access is important, but I will send you some of the information which I think may be useful to you. Now, at the end of it, why am I offering this course and why are you taking it? There must be some course outcomes. So let us try and see, at least from my expectation point of view, and what I would expect that you would be able to do at the end of the course, or at least certainly I would hope that you can do it. Firstly, I want you to gain and grasp the ingenuity of bulk, inorganic, chemical, and petrochemical and bioprocesses. None of these things fell from the sky. They had to be invented. And you must understand the ingenuity of the people who invented this. Also, that history sometimes has been very unfair to some people. One or two names get propped up. Like when we say Haber process, that's the only name you know, Haber process. Okay. How much do you know, for example, of all the other people who actually played a very crucial role, like Le Chatelier, Nernst, Ostwald, great minds. I mean, in some ways, their contribution may have been even greater than that of Haber. People who had developed other processes by which you can make ammonia is very important to know. Maybe those processes will get revived in the future. So don't just assume that Haber process means forever till eternity it's going to be Haber process. Okay, so that's the kind of ingenuity that I want you to grasp. Also, what differentiates, let's say, chemical engineers who join ICT? I mean, all of you are extremely bright. You have it is very competitive to get into ICT, and you'll have done. So I presume that all of you are extremely intelligent and bright. Now we have a yearning to look at things very deeply from a science angle. In earlier days, what you'll find is that many of the inventions were, of course, there was science, but it was not as if all the science was understood to be able to practice the technology. No, there's so many technologies which were introduced for which the science was revealed much later. In the case of the Haber process, the mechanism of catalysis, it came about 70 years later. But that didn't stop BASF from practicing the Haber process. It's very important that we also see the linkage between scientific understanding and technology. The best is if you have wonderful technologies and which are underpinned by very deep knowledge. Many times what you'll find is that you can have one level of technology and which you can introduce in a more phenomenological manner. But to be able to then perfect that technology, to make it better than what it was, there you will require much more thorough knowledge of let's say, things like thermodynamics, kinetics, other issues which you need to grasp, material science, because they are going to be so important to be able to then practice those in a perfect way. So that's where science and technology actually join hands, because it is that knowledge which underpins the technology development. Okay. I also want you to understand, as I said, what are the scope for improvements in existing processes. We won't be able to do it in all cases, but certainly in some cases, I would like to point it out. That where there is an opportunity for people and where you might actually focus your energies, if you were to, let's say, get into this area and become chemical engineers who are actually practicing chemical engineering and chemical technology. Okay, so that's very important that you gain this appreciation of room for improvement. The best of chemical processes are about managing conflicts. They will always be. I mean, it is in our personal lives as well as in chemical technologies that there will always be contradictions. There will be conflicts. You carry out an intervention and you find that something has improved and you start clapping, but you also find something has gone bad. Not everything is good about it, and it has become increasingly the habit. I find in numerous processes and papers that people are not balanced in the way they report things. They only report the good stuff and sweep the bad stuff under the rug. I mean, it's no point, you're just fooling yourself, right? So it's very, very important that we understand conflicting requirements in a process. Can anyone tell me if you can think of any such contradictory things that can happen from basic thermodynamics and kinetics?
Sir, could you please repeat the question?
Yeah, I'm just saying, as I said, I mean, we know that in many things you can have something improving. Okay, you do something, you change a parameter. Okay, something improves. Okay? But then you find that something else did not improve. In fact, if anything, it got worse. So I'm just trying to see, like, let's say from your understanding of thermodynamics and kinetics, and look at it in the most basic elementary way, can you see any situation where you can have some kind of contradictory things, that something improves and something worsens?
Sir, selection of a catalyst.
Yeah, and what about it?
So one catalyst may be efficient and other maybe not, but the one which is not efficient, it costs low. So we have to.
I mean, so you're saying that it could be cheaper,
yes,
right? Excellent.
So as another example, if we take the example of Haber's process for the manufacture of ammonia, we use it at an optimum temperature. It is not the temperature at which we have the maximum rate, but if we increase the temperature any further, the other conditions such as pressure and other parameters is very difficult to control. So we use it at an...
Excellent. So you are saying we make compromises, okay, compromises in terms of pressure in the Haber process, right?
Yes, sir.
That's what you're saying.
Yes, sir.
Brilliant. Look at, for example, an exothermic reaction. What happens if you increase the temperature of an exothermic reaction?
The conversion reduces as because actually the rate of the exothermic reaction also increases, but the rate of the backward reaction is also increased.
If you have an exothermic reaction, I'm forced to operate it at a lower temperature to guarantee a more complete conversion. But the moment I go to a lower temperature, the rate of the reaction can get adversely affected. So that would be a good example of a contradiction. Is that clear to you?
Yes, sir.
Yes, sir. Yes, sir.
Yeah. So rate versus conversion in exothermic reactions. What is really remarkable is that people have been very ingenious, and they've come up with clever ways of trying to circumvent these kinds of contradictions. And that is brilliance. Those people who were smart enough to look at these kinds of classic problems and came up with ingenious solutions. So we will discuss, for example, this kind of ingenious solutions when we discuss, for example, the contact process, the sulfuric acid manufacture. Okay, and I'll put student inputs. Okay, now we will try to analyze a process based on multiple considerations. Especially, you have to be very careful of salespersons. Sometimes, there's such smooth talkers, and they will always talk about all the good things about it, but not really looking at it from all angles. And if you're buying a plant, how would you objectively decide what you'll do? One way is, which is the copycat mentality. Everybody is doing it, so I'll also do it. Okay, which is typically what happens. That's one way. But you, as chemical engineers, can you apply your knowledge of the subject and be objective about it? That's what really, if you can do, it will be wonderful. So, for example, quality specification. There could be very demanding requirements. You'll find that some processes enable you to get that kind of quality and others don't. Even though it might be cheaper, but there can be serious issues. Okay, raw material availability. Someone sells you something and later on says, well, I can't guarantee you the raw material. What's the point? I'll be saddled with a plant, and believe me, this has happened. The Birla company, they set up a 50,000 ton per annum plant on magnesia production from seawater. I mean, they bought technology and they had to scrap the plant while it was being built, saying that no, these guys told us, we'll be able to do this, but we are finding real problems, in actually practicing this technology because of various requirements. Energy requirement. How energy intensive is it? And what kind of energy does it require? And where am I going to get it from? And will tomorrow somebody come and say, hey, you shut down your plant because you're generating too much pollution. Capital expenditure, everything is great about it, wonderful. But when you ask, hey, how much will this plant cost? I mean, people will run away. Okay, they'll get scared. Safety. Is it a robust process, or is it something which is very finicky? And if I just deviate here and there a bit, I can have an unsafe situation. Very, very crucial. Waste management. What are the waste related issues that I need to look at? So I must be able to analyze, and some of it, of course, you have to be able to analyze quantitatively, and some of it more intuitively and qualitatively, But all these issues must be there at the back of your mind. And if it isn't, somewhere you could slip up. And imagine if you are the project engineer and that responsibility is given to you, and you are not looking at it from all angles, you could be in for serious trouble. Today, nothing is more important than sustainability. Raw material sustainability, environmental sustainability. And when I say environment, in fact, there was an excessive emphasis on aqueous effluent. Everybody would talk about, I'm reducing BOD, COD. Many times, actually, you don't realize, but the guys are putting a lot of their effluent in the atmosphere. I remember, one of the classes we had gone to Bangalore, and they're some of the best practices, but it was very clear that some gaseous effluent issues can exist with that process, and many times these are quietly forgotten. So vitally important that you look at it, and many times when people tell you about some effluent management protocol, you have to, and they try to deceive you, saying that you do this and you find that your BOD, COD is coming down. But nobody is doing a proper mass balance of what you started with and where all it ended up. Those are the kinds of things increasingly. Today you'll find you'll have to worry about not just liquid effluent, you'll have to worry about gaseous effluent, you'll have to worry about solid effluent, and then liquid effluent, where all it can pervade and percolate. Okay, and so these are extremely important. And of course, we all know about climate change and those kinds of issues, which are exceedingly important. You must also be able to, this is, for example, something that the company BASF, and not just BASF, some of the greatest chemical industries were so good at doing that they invented a process which was a fantastic process, and they would have kept saying, where else can I apply it? Where else can I use it? So you start looking for commonalities between processes and trying to see how you can transfer knowledge from one domain to maybe what would appear to be a completely different domain. And obviously you can cut short on time by being able to do that. So draw correlations among various processes, looking for commonalities and differences. This could be a very useful thing for you to pick up. And also at the end of it, I would love it if you can gain some kind of mastery of preparing case studies of practical problem solving related to chemical processes, and also try to build future scenarios as part of those case studies. Frankly, if you had a little more time, it would be good to give you all some problems related to case studies. Let me see, it may still be possible to do that. What I will also do is try and have at least one or two people from industry who can come and talk to you, okay, about some of the technologies that they practice. So if you can organize those, then that will be nice. Let me see if I can do it. All clear about everything that you have listened to till now?
Yes, sir, it's clear.
Okay. Now, what we'll do is that I've taken this from the book of Fred Aftalion. It's really remarkable. If you look at, as we know, civilization has existed for thousands of years. But if you look at some of the very dramatic changes that have happened, let's say, over the last 200 to 250 years, is breathtaking. Maybe at a later date, you may question whether it was all for the good or not. But just so that you get a feel for the pace of change. Let's just see the kind of changes that took place. Aftalion says that 1829, when his great grandfather was born, at that time the telegraph was not in place, and the telegraph is not there today either. So it is something that has came and it has also disappeared. The steam locomotive and steamship, again, it was not there. These were the things which were considered to be great. They've all disappeared. I mean, except for a museum, you don't see a steam locomotive anywhere now. They were barely in their infancy. It's surprising, but the concept, the chemical engineering branch, actually came a lot later. And chemists and chemical engineers had not even embraced Dalton's concept of atoms at that time. We know that even the Dalton's concept of atoms was not the perfect description of the atom. So many things have happened since then, but it's all happened. Okay, you can see that it's not even 200 years. Okay, look at the remarkable thing, and because we are taught in a very sterile manner, we are all taught what is there. Okay, we just take it for granted, but they didn't exist. Now, 1856, when the author's grandfather was born, okay, he says there was neither the telephone nor the electric light. It didn't exist. The periodic table was not well known, the periodicity of elements. And even after Mendeleev came up with it, we know that there were plenty of flaws, and it had to be superseded with a better understanding of the periodic table. And we are talking about barely 170 years. 1893, when the author's father was born, there was neither the radio nor the aeroplane. Automobile was a curiosity at best. In fact, there was a time when we were working with Daimler-Benz, the Mercedes-Benz group, and they had invited me to their headquarters in Stuttgart. They showed me this is the first automobile that was built by Daimler and Benz. I mean, it looks more like a rickshaw, okay, but that's the first automobile. What a remarkable transformation has happened over the years. For example, the structure of matter and radiation were really just beginning to be understood, but it had to wait the knowledge that was provided by Rutherford, which came later. And so, even then, 1893, we are talking about what? 130 years or thereabouts. That was the situation. 1928, when Aftalion was born, there was the electronic era had still not commenced. Neither the transistor nor the electronic computer existed. We are talking about what? Not even 100 years. The genetic code had not been cracked. Today, if there's so much of drug discovery which is being centered around understanding of the genetic code. It's so important. Space odysseys were science fiction. Okay, even then. And today, I mean, we are talking about people having, now space tourism, okay, is becoming common. As you know, the latest initiatives over the last couple of months. It's just amazing what has happened. Hopefully, it will become sufficiently inexpensive that all of you will get to see our world from space, maybe in about 30, 40 years. It will happen. So why did it happen? Why did such a dramatic transformation take place? It is all because of revolutions, that the rise of the chemical industry was linked to certain revolutions. Of course, people lived. There were people there. Okay, I mean, if you look at the way people did farming, people survived. Okay, it was going on. But what happened? The two triggers. One was the American Revolution, the War of Independence, and the French Revolution, where they declared the rights of man and citizen. I mean, read man and woman. Man doesn't mean only male. It means everybody. Okay, and what it was, everyone started saying, "Hey, I'm also no ordinary person. I'm also king. Not only the king is king, but I'm also king." And that actually spurred demand for goods. Everybody then aspired for a better life. And so the moment they started aspiring for a better life, at that time, people realized that the old ways of doing things is not going to enable them to reach that. It's just not possible. And it therefore is what really catalyzed the Industrial Revolution in England from 1760 to 1840. The Industrial Revolution, one of the hallmarks of it was the revolution in chemical industry. Chemical industry really touched the lives of people, in a way that many others didn't. And that went on all the way from the middle of the 18th century, the entire 19th century. There were one chemical revolution after another. In terms of the ingenuity and the understanding, everything happened hand in hand. And there was also no snobbery that, hey, I'm a fundamental researcher and you are a technologist. No, they all work together. They evolved science out of a necessity. And that's the way things happened. And even in the 20th century, the chemical revolution continued. Things like quantum mechanics, etc., were the creation of the 20th century. The electronics revolution happened in the first half of the 20th century. It was spectacular in a period of 200 years. What happened? Now, if you ask me, have we kept pace with that kind of a speed of revolution? I would have to say no. Of course, we have perfected technologies, but in the terms of the sheer breadth of innovations and inventions that took place from 1750 to let's say 2050, I feel we have slipped up somewhere, and we have simply not done as well subsequently. Even though we have got far more things available to us, to help us. I would take, for example, the case of catalysts. The greatest catalysts which were invented by about the 1950s, 60s. If you ask me, what are these extraordinary catalysts that have been invented since? I mean, I would struggle to name that many as one would have had prior to that. So don't get fooled by all this talk about how fast, super fast we are moving today. It's simply not true. The fast and the super fast is more about reaping the fruits of many of these things. But in terms of breadth of innovation, invention, I feel that we are lagging behind. Contrast that with the early part of the 18th century, when in fact the American and the French Revolution had still not gained a foothold. There was really no such thing as the chemical industry at that time. The other thing is that people did things. Of course, they did things and things worked, right? But many times they didn't know why it works. But they did it, and it worked. Like for example, someone figured out that you can take animal fat and ashes of plant, cook them up, and you'll get soap. That's great. They found that out. They experimented with roots and barks and found that some of them had therapeutic value. They were able to make glass. They didn't understand the details or structure of glass. Most of the colors were natural colors. The fertilizers were manure, and even the preservatives were of plant origin. So the key thing is that they did not understand why or how these substances work. What happened after 1750 was this fantastic development of science and technology going hand in hand, and where they started asking questions like, why does it happen? How does it happen? Science and technology really progressed in dramatic synergy. since 1750. And when we look at some of the technologies, you'll get a feel for that. And look at it, 200 years ago, as we said, the basic mysteries of matter had not been worked out. How do you expect that at a very fundamental level they would be able to do it? Does it mean that they didn't do anything and they just sat there doing nothing? Not at all. And there is a lesson also in that. I feel that especially chemical technology, let me tell you, there is a lot of excitement in actually trying out things and doing things and finding things. If you get stuck in the mindset that no, I will understand everything before I do it, then I'm afraid that the pace of development is not going to be as fast as what we had in, let's say, the 19th century, and especially in the 19th century. The other thing is that chemistry really did touch people's lives, because they had clothes to wear, they had better clothes to wear, they could look beautiful. There was a lot of, they could treat illnesses, such important things, they could feed people. So it really touched the lives of people. The chemical industry, and particularly chemistry, had a massive role to play. But the thing is that all of them saw the front side, the front end of the technology. Everybody saw the products and they loved the products, but they did not see the back end. They did not see the waste that was being generated. At one point, this knowledge dawned that, hey, there is also a back end which is not so attractive. It's got an ugly face to it. And the media became powerful. They started sensationalizing some of the pollution problems, etc. And suddenly people were gripped with fear. And chemical industry became, I will say, a bit of a bad word. And that has not really got erased from people's mind. So everybody loves the goods, but they also do not love all the things that they hear as the not so good things about the chemical industry. Let me tell you that part of the reason for the slowing down of progress was that freedom to experiment had gone, because people would ask safety issues. Is it safe to do it? Is this process safe? Would I be generating a lot of waste and pollution and toxic stuff from this process? And if the answer was not a clear no, people said, wait a minute, I will not let you get into this. And that's how partly this kind of rate of progress, of innovations in chemical technology actually went down. Of course, this Fred Aftalion is critical about it, but the truth of the matter is that there is no getting away from the fact that there was a dark side to the technology. Okay. Now, let's look at a little more in terms of some of the very, very key things. Two very fundamental changes. One was, till that time, wood was the source of energy. You burned wood, and it was really, these biofuels means primarily wood. But the big change was the switch over to coal. The moment you had coal in abundance and with a high energy density, it just revolutionized manufacture. That was one. Okay. The second was that people would actually manufacture more in their homes or in small communities. There was no big industry that existed, and all the tools were hand tools, which they would machine with their own hands. But once people realized that this kind of production is not going to let us produce at that kind of a scale at which all people can say, hey, I'm also king, I also want the goods, that the need for machinery and factories and mass production became more and more it came to the fore. Once you talked about machines, that gave rise to the iron technology, because all these machines required good materials. It required steel, it required iron, and so there was a massive surge. Biggest aspiration was clothes. People wanted to look good. Whatever cotton, etc., they were using, they wanted those cotton clothes to look nice and white. If it was white, they didn't want dirty looking clothes, things which look brown and yellow. And there was a revolution in textile industry because of that. And that in turn led to a massive spurt in the kind of chemicals like sulfuric acid, chlorine, caustic soda, soda ash, and all of it was driven by the importance of textiles. And of course, one of the great other things was the steam engine. Why? Because till that time, people just worked wherever they were born. They were there. Nobody had this mobility. There was no mobility of goods either. But once the steam engine had been built, people realized, oh, I can transfer things. I can transfer raw materials. I can transport products by long distances. And so, it was vitally important. So all of the things fit in beautifully. All of the aspirations of the people were really met because of the profound things that happened in these particular areas. Now let us look at the what happened which was not so good and which we are paying the price for now. Now this is really the record of carbon dioxide in the atmosphere. Don't worry about how exactly they were figured out, but I can tell you that there's a profound role of things like isotopes. People used to actually monitor frozen ice. There would always be some air which would be entrapped in the ice. And that used to be the signature of the atmosphere at that point in time. And so by analyzing those, you could infer that really what was the kind of atmosphere that we had then. So what you can see is that from the time of the birth of the Industrial Revolution, which was around 1750, thereabouts, you can see there was a distinct upsurge in the carbon dioxide accumulation in our atmosphere. And look at it till then, fairly flat for thousands of years. I mean, this only goes up to 1,000 years. But, I can trace it back to 5,000 years. It would look much the same. There's no difference. But look at how distinctly it started going up. So all that so-called burning of coal, etc., which were the proud moments of the Industrial Revolution, we are now paying the price of what it meant. But if things were bad then, look at what has happened in the last 50 years. You can look at it over here and here. You can see that this slope, which was like an exponential growth over here, and there is clearly a steep change in the slope. And the slope has become very sharp. This is from when? This is all from 1950, and especially since 1980, there has been a dramatic, steep increase in carbon dioxide levels. So much so that, the level which was somewhere between 250 and 275 ppm, in the atmosphere, today stands at 415 ppm. That is the reality. When I'm burning wood, the carbon, is one type of carbon. When I've got fossil fuel, the carbon is a different type of carbon. Why? Because any natural material, natural carbon, like the carbon, the wood that you have today, will always have some amount of carbon 14. which is radioactive. And you know that that's how they do carbon dating. Whereas a fossil fuel, all that carbon 14, because carbon 14 doesn't have a very long half-life, it's a few thousand years. So fossil fuel means all of that carbon 14 would have gone. So what I have to look at, what has happened to the carbon 14 levels? The carbon 14 is going down because the fossil fuel burning has gone up. And so by monitoring some of these isotopes, you can get a good feel for actually that this CO2 rise is undoubtedly because of anthropogenic activities. There are a lot of people who have been questioning even today. People say, no, these have got natural causes. But you cannot deny the isotopic signature of the atmospheric CO2. And we know from that it's really because of the burning of fossil fuels. Now, people have been trying to reverse it. And that is the trend. And look how interesting it is that England, who were the people who led the Industrial Revolution and the pride of having introduced coal and the burning of coal. And look at this. Britain goes coal-free as renewables edge out fossil fuels, 10 June 2020. Today, there's just about 2% of usage in the entire power portfolio of England. The use of coal is just about 2%. But what has happened now? There has been such a shortage of things like natural gas that England is now being forced to rethink that whether it has to restart its coal plants. So you can see the tug of war. It's all great to talk about environment and how we must get rid of coal, and the whole world is talking about it. But when it has come to the crunch, people have said, but standard of living is as important. And so people are paying lip service to the environment, and quietly they're trying to revive the use of coal and natural gas and everything else, simply because they're saying, hey, if we don't do it, we'll all be doomed. We cannot let mankind be doomed. And so there is this tussle between the Greens and Gross Development Product and things like that, which have come to the fore. I mean, that is today the reality. Let us also look at side by side with this technology, steel, this, that, everything that we talked about. Let's look at the landmark discoveries that were made. And look, it coincides with the birth of the Industrial Revolution and the American and the French Revolution. And what an amazing thing that, can you imagine that first we are talking about, say, 1766, when hydrogen was discovered, and hydrogen was discovered even before the discovery of oxygen, which was almost 10 years later, and Lavoisier basically having to overturn the phlogiston model. The whole concept of actually what are compounds and chemicals and how they are transformed from A to B to C, all happened around that time. Look at Humphrey Davy, 1778 to 1829. They're talking about what? Talking about 50 years? And one person discovered several of the alkali and alkaline earth metals. One person contributed to the discovery of chlorine and iodine. Have you heard of any modern day scientist who can claim anything remotely in terms of grand success as what, say, Humphrey Davy achieved? Or take Berzelius. He found out the atomic weights of the first 40 elements. Berzelius also discovered, 4 of the elements, including silicon and thorium, and selenium and cerium. He is the one who proposed the term halogens. He is the one who conceived isomerism, without which, today you cannot think about organic chemistry without the concept of isomers. And it is Berzelius who for the first time conceived of the idea of a catalysis. We will go a bit more into that. And mind you, he did all this without doing a single experiment. He would be sitting somewhere and reading literature and trying to draw common knowledge from some of the observations, etc., which were reported by scientists. This is another thing that you should keep in mind. Every time you need not do experiments. If you are a smart guy and with all the literature around, if you can scan literature, there are great inventions and discoveries to be made. So do not neglect it. Do not think that I have to do an experiment in the lab. Not necessary. Okay? There are people who have done great things. Look at then Berzelius. He is the one who also, till that time, all transformations were done by heat. You heated things. Okay? It was Berzelius for the first time who also said that you can actually decompose matter by electricity. One person, can you believe this? And so that was the extraordinary mind that you had in those days. I have not seen anything close to it, not even 1% of it, anything in the modern era, notwithstanding all the talk. Look at the periodic table. This was Mendeleev's periodic table based on atomic weight, mostly in the early 1900s, 120 years ago, came up with the periodic table based on atomic number, and it changed everything because now you could arrange elements in a systematic manner. But that, if you see, there were many gaps in the periodic table even then, and the highest known element was 92, uranium 92. And it was the quest to basically see if there can be elements beyond uranium 92, that the whole thing of nuclear power, nuclear war, everything was born out of that. It was the quest to identify elements going beyond uranium 92, which was done by Enrico Fermi. He is the one who propelled this work. And then you just see how many more elements got discovered and how the periodic table completely got filled up. Let us look at the bridge between inorganic and organic chemistry, and the birth of organic chemistry. Interesting, organic chemistry, the name actually is because of things which were produced by the organs. And who was it who produced something from the organ? It was Roell. He is the one who had the smart idea of taking urine and evaporating it and then being able to get some crystals. He got these crystals, which he called urea because it was from urine, and people forgot about it. He didn't know the structure of urea, but he called it urea. Now, Wohler was an inorganic chemist, and he was trying to do simple inorganic reactions. What was the reaction he was trying to do? He wanted to take silver cyanide and ammonium chloride, and he knew that silver chloride is a very insoluble substance. And so he thought that if silver chloride were to precipitate, then he might be able to push this thing forward, and that he would like to make ammonium cyanide. That's what he wanted to do. He wanted to make ammonium cyanide by double displacement reaction. That's it. Okay. But then what happened was that when he started looking at the properties of this, he said, hey, and how would he have looked at property? What could he have done in 1770? There was no NMR. There was no infrared spectroscopy. There was nothing. Okay. What did people do? They would measure melting point. Melting point was provided an identity of chemicals. They may have done elemental composition analysis, that they probably knew how to do. He checked the melting point, And what else? I can look under the microscope and look at the crystals, how they look, their shape, etc. And he looked at the melting point. Probably, I don't know. I presume that's what he did. And he said, "Hey, this stuff is the same as what Royal made. It's got the same melting point." Maybe he peered into the microscope and said the crystals also look similar. Okay, and he then wrote that I can make urea without the use of kidneys, either man or dog. Ammonium cyanide is urea. That's what he said. And it was later that people found out that ammonium cyanide is not a stable molecule. And it decomposes to NH3 and HOCN and further recombines to form urea. And so this urea, which Royal had found, and this urea, which Wohler actually had found, but actually didn't elucidate the structure of, they were the same. But remember that Wohler is excessively credited with this whole process, where in fact we forget the role of Royal, we forget the role of the others who actually characterize urea from ammonium cyanide from this reaction. So I told you that look for similarities in processes and technologies. Now look at this. This is a very interesting thing. The photo that I've shown you is the photo of an immersion explosive. After the days of Alfred Nobel, when so many people died, there was a constant move to make safer and safer explosives. And one of the explosives that people came up with, although much later, was immersion explosives. Is really you can think of as an immersion of ammonium nitrate solution in oil. So you have got the fuel and the oxidizer. But that explosive is a dud unless you introduce gas bubbles. And it is the gas bubbles which provide the sensitization. I don't want to go into the details of how it happens. How it is done. That ammonium nitrate which was being taken as the oxidizer, towards when you make this explosive, it becomes a putty-like viscous mass. Okay, I'm not going into the details. So people said, "Hey, let's see if I take sodium nitrite, just the same way that ammonium cyanide was made, and I do a double displacement, what happens?" Okay? It ends up forming ammonium nitrite and sodium nitrate, driven by the high stability of sodium nitrate, and this stuff decomposes to give you nitrogen and water. And it is the nitrogen gas which gets entrapped in the explosive, and that's how it becomes an explosive. So you can see an example of how knowledge can be made to flow from one thing to the other, from something as profound as the discovery of urea through a simple double displacement reaction, entirely constructed with inorganic chemicals, and the gassing of immersion explosives to make the latest generation of explosives. That's what was done. Let us go a bit further and look at how basically from alchemy people moved over to chemistry. We will not be covering, of course, all of this. We'll be covering some of these, okay? But probably the most important over there was Lavoisier's role when he actually was able to explain the process of combustion and overturned this belief that some fire-like element comes out in the course of combustion, which they called as phlogiston. And he was the first to figure out how combustion takes place. And not only that, he also came up with the concept of what they call burnt air. You'd never hear that term, that air is burnt. What does it mean? That after that, it has lost its fire-giving property. It has lost its life-giving property. Why? Because the process of combustion used up all the oxygen. And so it was called burnt air. That was the name for air without any oxygen. It was called burnt air. the role of textile bleaching and how it had a massive impact on first on sulfuric acid and later on alkalis and also on chlorine. It was phenomenal, and the entire chemistry started getting understood. The advances in chemistry that I talked to you about, the work of Berzelius, the work of Dalton, Avogadro, laws of electrochemistry, Faraday, name it. That was a genuine advance in chemistry. Very profound. People knew that fat you can treat with plant ash and you'll generate things like surfactants, etc. But nobody really knew what exactly was fat, what exactly was rubber, and it was these understanding that led to the dawn of synthetic organics. As we discussed, people used to use extracts from plants as dyes. People knew that. You go to Ajanta Ellora cave, you'll see in Ajanta the beautiful paintings. They are all from natural dyes. But the moment people realized I can make synthetic dye stuff, and the first one probably was Movine, which was a sea change, a color that was considered the color of the aristocrats, purple. Purple was aristocrats' color. And everybody could afford purple. Purple became the color of the masses. What an amazing transformation. I think purple, the Movine, and I will say aluminium, which at one time was much costlier than many of the other metals, and how the cost of aluminium came down. Of course, you know the process, but we'll discuss it in a bit of detail. Amazing things which made the royalty look ordinary and made the ordinary people look extraordinary. Coal tar products. People realized that coal can be transformed into other kinds of substances which can be extremely useful, and coal is not just about burning and converting into CO2 and heat. Coal is more. Coal can give chemicals. And that was the great work of the French. It was the French who really led the work on coal tar products. The explosives, the moment you had explosives, the entire area of weaponry, the entire construction industry, because I could demolish things, I could make tunnels, I could break apart mines and get minerals and ores from those mines. I could do all of those because of explosives. Otherwise, I couldn't do it. That was a tremendous thing. And also, I think the great understanding that was provided by Alfred Nobel in understanding why, for example, nitroglycerin is an explosive. Phosphorus and the use of matches, matchstick. I have everything, but unless I can cause a spark, I cannot create a fire. And the use of matches, these were the great, great inventions. And the understanding that phosphorus is a very crucial element which you can burn and you can ignite and create fires. Common salt from the work of Leblanc, which we'll discuss, that as such an important feedstock. People said NaCl is not just about eating. NaCl, we will see, how that whole process of discovering soda ash, etc., happened. But what a phenomenal invention! The two inventions of generating soda ash and also subsequently generating caustic soda and chlorine from common salt, remarkable. And people understanding from that what really is the chemistry behind formation of acids and alkalis, and how salts get produced from acids and alkalis, and how it's possible to reverse that process as well, to convert salts into acids and alkalis. It's not a one-way street. I can move in either way. And that's what they showed. And I was telling you about the French and the coal tar. And what did they do? They were able to liquefy coal. Okay? And mind you, the moment they liquefied, okay, they also found that in the gases, they got ammonia. And the first fertilizers were made with that ammonia, which came out because of the liquefaction of coal. And simultaneously, they could do controlled combustion and come up with syngas. The moment they got syngas, they knew that, oh, I can separate it out. I can get carbon monoxide. Moment I've got carbon monoxide and chlorine came later on, I could make things like phosgene from the reaction of carbon monoxide and chlorine. I could make acetic acid. I could make so many things. Or I could use it in internal combustion engines. I can run those engines through syngas. I can make methanol, acetic anhydride, name it. And it opened up the floodgates, of chemicals. The lesson is that although today we get almost all of these chemicals from crude oil, do not for a moment think that you can't get it from coal. And the reason why I'm saying this is India has got a reasonably good reserve of coal, whereas India doesn't have oil. It's exhausted everything. There's virtually nothing there. So keep these in mind, and these kinds of technologies are likely to become very, very important in the coming years again. Any questions before we close?
Sir, do we have to remember names and years?
No. Some things like, obviously, you should know the span of the Industrial Revolution and those kinds of things which are so landmark. You should know. But otherwise, no, I'm not going to test your memory. There's nothing wrong in remembering some years and things like that, because they're just like you don't forget your date of birth, or that of your parents or your siblings. Similarly, some things which are so fundamental to the entire growth of the chemical industry, at least some of those essential dates you should remember, some landmark things. Okay?